Hi, my name's Lucas Marsh, and my group did our project on tracking maneuvering targets. My group is comprised of me, Brandon, Logan, and Louie. So the background. Tracking maneuvering targets is an important topic utilized in a multitude of different fields in the real world. Often, target tracking is utilized in transportation methods, missile launches, and a plethora of military purposes. All those clips that you always see online of the helicopter using a radar to track somebody who's running around. Often, it's more so done through thermal heat tracking, estimated projectile movement, which is the base of what we're going to be using in radar tracking. So ours is going to be obviously a very simplified version because the technology has gotten so advanced in this field. So the preliminary analysis, our group used MATLAB to create a guided user interface where users can input the values of components of tracking motion. The program consisted of a tracking variable, a random number generator for repeated results, and a defined scenario by the user and manipulation of process noise. Utilizing these applications, a multitude of graphs were generated to compare the accuracy of tracking motion. The distance between the true and predicted state was calculated and represented graphically, making standard error graphs. All of our final data will be represented graphically and with the data normalized from differing process noise. So first off, to be able to actually do this, we need to create the scenario. The scenario that we're going to be using here is a very simple scenario of a single target that is initially traveling at a constant velocity of 200 meters per second for 33 seconds. This object then enters a constant turn of 10 degrees per second and does an entire loop. The turn lasts for 33 seconds, and the target accelerates in a straight line at 3 meters per second squared. So this is three different phases of this one scenario. The initial phase has a acceleration of 0, so it's just going to be moving in a straight line, and that's how the first and the third phase are different. To do this in MATLAB, you first, of course, have to define our velocity, which 200 meters per second, the angle, omega, 10 degrees, and the acceleration of 3. dt is our time interval, at which 0.1 seconds every single time is going to basically, the tracker is going to take a snapshot of this so that it's accurate results, and TT is going to be used for creating an array to be able to store all these values in, and then figs is just the base for how we're going to make all of our figures. To be able to do this, we need to define an array xgt and use numal, which returns the number of elements in that array, and that array is made up of NaN values, which are either single or doubles, so that we don't get any values that are incomprehensible to the computer. We're going to utilize a ton of for loops at the differing intervals based on TT to create the three parts of the scenario, so that it'll keep on overlapping until the 33 seconds is up, and then it'll start the new scenario. All these intervals are going to be defined as x initial or x1 based on the x position and the amount of seconds that have gone by that tell the object of which phase it's in of the scenario what it needs to do. Using this, we're able to get our true position scenario. As you can see in blue, it starts off, there's no acceleration, so the x position just stays at 0. It moves at its 200 meters per second, and then in the red, enters the constant turn phase where it does its 10-degree turn for 33 seconds, and then at the end it does its constant acceleration of 3 meters per second squared. So now we're going to make our randomly generated seed to be able to just make a bunch of different types of these scenarios, and then we're going to set up our first actual tracker, because right now all we have is the actual true position of the object. So on our left, we just have the little setup for our randomly generated seed, to be able to just make be able to make all the different random setups that we're going to use. And on the right, we're going to use a constant velocity filter. Now to do this, we're going to use an already defined program in MATLAB called tracking EKF. And we're going to define it using a constant velocity motion. Tracking EKF is a filter used to track dynamical states through position and constant velocity calculations. So it's a very simple form that's pretty easy to define in MATLAB, that you just use tracking EKF, and it immediately has an entire program set up for it that's already been completed. For each measurement, you predict the filter, calculate the distance of the predicted state from the true position, and correct the filter using the measurement to obtain the filtered estimate of the position. And that yields this first image over here on the left. As you can see, it is direct on for the constant acceleration and the constant velocity parts, phase 1 and phase 3, since it knows exactly where it's going to go and what it's going to do, and there's no deviation in any acceleration or anything. The hard part is, of course, tracking the turn. The red area is the actual turn in which the constant turn is made at the 10 degrees per second, and the green is it trying to track the turn, but since the acceleration is constantly changing in this area, as you can see, it's not directly on. There's little gaps in between that change it, and the graph on the right shows the normalized distance from the estimated position to the true position. As you can see, there's a massive spike after 33 seconds whenever this phase begins of it not being exact on the position of what we want it to be. To be able to solve this, we need to increase the process noise as a solution. Process noise is the amount of uncertainty in the calculation of the object's motion. For a constant velocity model, these are the unknown acceleration terms. So as stated prior, as it's going through the 10 degrees per second turn, the acceleration is constantly changing, making it, allowed to do that turn. By increasing the process noise, we're allowing for larger uncertainty in the motion of the model, which causes the filter to rely on the measurements more than on the actual model. The following lines create a constant velocity filter with high process noise value that correspond to a 5G turn. So we use the distance and zero it from 1 to the number of steps. We use estimated position and do the same thing. And once again, we utilize another for loop that's making it predict where it's supposed to be rather than actually just looking on the measurements. Rather than actually just looking at the model, it's going to rely more on the measurements of what it should be at so that it can calculate the exact position. And as you can see in this cyan color, it is much more accurate as it goes through. They're all on top of each other now, so it's a little bit harder to see, but it's able to track the position much more accurately throughout. And on the right, you can see that the difference in where the light green was of how it goes all the way up through the normalized distance of it unable to tracking it. It this time doesn't go nearly as high to be able to track it correctly whenever it's in that constant degree turn. But as you can see over on the left at the start, since instead we're using just predictions of where it should be, the predictions can be small numbers off, like 0.01 meter, 0.1 meter difference, which allows for a good tracking in the constant degree turn. But in the starting phases and the third phase, well, in the third phase is better, but in the starting phase, there's difference even though the velocity is just 200 meters per second and it just keeps on going in a straight line. Since it's doing calculations instead of just trying to look at the model and guess the right spot, it's a little bit off because it's much easier to just look at the model and be like, yeah, it's just going in a straight line. So the conclusion that we have for this is obviously an extremely rudimentary method of tracking an object's movement. There are obviously much more advanced methods utilized to yield much better results than our group was able to fabricate, but we were unable to do that at MATLAB because that would require a whole lot more time and much smarter individuals than ourselves. This process represents basically the foundation used to track the motion of an object. And most of this stuff is typically utilized in military purposes now. And for our contributions to this, I made the video that you're now watching. Brandon contributed by finding the application on MathWorks and deriving it with me, which took a long time. Logan contributed by making the PowerPoint and the script for this video, and Louis contributed by proofreading everything and basically being our coordinator for everything that our group was going to do. And he also helped out in deriving some areas that were much more complicated in the actual code. And that is it for our group presentation. Thank you.